Oh no. What the heck? Oh no. I sort of feel like my hardware is limping to the end of the semester. I think I should punt. Oh. All right. I give up. All right. So let's see. I had a few little administrative things. The extension to MP7 is real. There it is. We decided to keep the extra credit due date the same because it shouldn't take you very long anyway, and this way you get additional full grading runs. Let's see. The exam policy, let's see, was sent to you. So exam 7 starts in just a few days. It will be your makeup exam. You will definitely have your scores for exams 5 and 6 before you have to make a decision. You make your decision when you're in the testing center, and basically you can just open up one of the exams. So you'll have the opportunity, you'll choose which exam you want to do. And you can choose whatever. You can choose the one for which you think you will increase your score the most. You can do all that math. Those are weighted averages. You can figure out for yourself which exam you should take based on how difficult you perceive them to be and your score. Let's see. The final for this course will also be in the CBTF. It will be kind of a combination of quizzes and programming, or quizzes and exams that you've seen so far. I don't yet know how much of each, but I think it'll be about half and half. It's a 3-hour exam, so it's kind of real. The good news about it is that it is the very first part of finals week. So you will be done with this class completely fairly early in the finals week process, which I think is good. Yeah. Oh, sorry. Yeah, okay, well, it's their fault, not our fault. Yeah, exactly. Okay, let's see. Oh, and I'm going to discuss a little bit more about the format of the final and what you can expect after we decide on it, which means within the next few lectures. Okay, so, oh, the other thing is that quiz 11, the one that we missed, we're going to release as just sort of an open exercise on Prairie Learn. It's all about AVL trees, and I'm not sure when that'll happen, but we'll let you know for sure. And you'll have kind of a lot of time to address the problems. So it's sort of intended to be a take-home quiz. You go. Yay, yeah. I'm not actually going to say the phrase work together on it because that would be weird, but we're not going to be able to tell if you don't, so I'm not going to say don't work together. There, how about that? Okay, so what is this? What is this? What kind of tree is it? It's an up tree, good. All right, so this is an up tree. I can tell by looking at it, but what's the connection to this picture of this up tree and memory? That is, how do we implement the up tree? What does the implementation of an up tree look like? What structure do you use for it? An array is correct. So it's implemented with an array. Let's see. Well, that answers part of my question. What do we use it for? That is, what does this up tree represent? Yeah, it represents a set. Represents a set. And suppose I have a forest of up trees. What do they represent together? A collection of disjoint sets, right, good. So a forest of up trees still implemented in an array, we use to represent a collection of disjoint sets. And what's an application of disjoint sets? What is something that we can use disjoint sets to represent? An idea from CS 173. What was the motive? Yeah? Yeah, we can use them to represent equivalence relations. Their definitions are essentially the same. Equivalence relations. Now, I don't know about you, but we've spent we spent a good amount of time a couple lectures talking about this abstract data type, disjoint sets, and this sort of uninteresting application, equivalence relations. Oh, did I really say that? I didn't mean it. It's not uninteresting. This application, equivalence relations. But you should, at this point, be a little bit curious of why are we doing this after all? It feels a bit like this particular abstract data type, ADT, came out of nowhere, right? Like it's just, I don't know, it's just a random choice of a data structure that we must need to study. Well, here's what's going on at a meta level. We're giving you a few data structures real quick that will be useful to you as we study graphs. So they feel like there's like these disconnects, but we're giving them to you because they're going to be useful to us in designing algorithms going forward. I'm mostly going to leave it to you to recognize at these sort of key points when we've got a problem to solve, wonder how we should solve it, and you will be the ones that will say, oh, I know we could use disjoint sets, or I know we could use a priority queue. Okay, so we're giving you these tools to help in designing algorithms for graphs, basically. So that's where we're headed. Now, let's go back to disjoint sets just for a few minutes, okay? Last time, we had talked about our two operations, find and union, and we had come up with a modification for union. We called them smart unions that assured us that the height of any up tree would be no more than logarithmic in the amount of data that our structure holds, okay? So we were in pretty good shape. But we had not yet used the find function to possibly reduce the height of the tree. And that's what we're going to do next. So imagine that we have this tree and we do a find of 4. We can get to 4 immediately. But the find of 4, what should it return by looking at the tree? What does find of 4 return? It's representative of its set, which in this case is 10. So find of 4 will return 10. Now, we're going to make an inductive assumption that it already has, and that inductive assumption is going to serve us well when we design our recursive solution to the problem, to the algorithm that we're going to implement here, okay? So, find a 4, we know it's going to return 10. Now let's execute a find of 4 as we understand that it works. So find of 4 starts here. I know it's eventually going to be 10. So before I walk up the tree, I'm going to go ahead and make that assignment. I'm going to redirect 4's parent to be 10. And then I'm going to carry on with the algorithm. The algorithm says walk up the tree. That is, do a find on 2. And then I'm going to do that recursively. I know where the root of the tree is, right? I know already that it needs to be 10. And so I'm going to assign that to be 2's new parent. And then continue on with the algorithm. Walk up the tree to 7. I'm going to assign 7's parent to be 10. Walk up the tree, assign 9's parent to be 10, even though it already is. Walk up the tree, hit the base case, we're done, return 10. Okay? Now look at the resulting tree. Yeah? So we're going to do this algorithm every time we do a find. So we are going to, what's happened here is that I wanted to illustrate that the tree could have been bad, right? Like, let's see. I mean, this one doesn't even look like it had very smart unions necessarily, right? I don't know how this tree was ever made. I just wanted you to see what our plan is for building it. And the idea is, so just forget about the meaning of the original tree. Okay, is that all right with you? All right, so the idea here is that any tree that we walk up, we're essentially going to draw up each of the vertices on our walk up the tree so that their parent is that root. So look what that does to this particular tree. 10 is still the root, and then it has 5 children, right? They would be 9 and 7 and 2 and 4 and 11. I'm not going to draw this whole thing for you. I'm basically replicating the arrows that I just drew. And then, you know, well, I might as well. 1 still is here. 7 has 8 here. 2 now has 3. 4 has 5 and 6. And 11 is here. So we've just shortened the tree significantly. This process of reassigning the parent every time we have an opportunity is called path compression. Okay? Yeah? Mm-hmm. Mm-hmm. Well, you have programmatic control of everything as you do the process, right? And that find of the parent is a recursive call. So you get to make the assignment after the recursive call returns, right? So we'll look at code in just a second, okay? Any other questions about this? I think what you're asking about is how does that code work? And I have the code, so I'll show you in a second. Is there a question about how this works functionally? All right, and boy, I don't know how you feel about this tree, but I look at this tree and I go, oh, this is nice. What a lovely tree. If we did a find on 3, it would ultimately mean that 3 would then move up and point to 10, right? Okay, so let's look at some code to do this. Here's union by size. We're going to start here. We're going to start with union by size. We haven't changed that code since last time. What's the running time of union by size? Whatever, whichever one. They all are the same. What's the running time for the union? Constant. That's right. Don't forget, the fancy union makes the finds fast. So this union is constant time. It's just a couple of assignment statements inside a conditional assignment statement, okay, all of which is constant. On the other hand, in our old story, this kind of union meant that find was log n. Now, here's the deal, though. We don't want the old find. That's the code I've written there. We want to modify find so that we change the parents as we walk up the tree. How do I modify that code? Yeah, good. So cover up the parent, or cover up the return statement for just a second. Okay, I'm going to put my finger over return here. You kind of can see me do that. Look at that. Oh, okay. Pretend return isn't there. Okay, that's the best I can do for covering it up. We know that we want this function to do this. We want the parent of node I to be the result of the recursive call, right? Do you see that? Okay, no surprise. That's kind of how inductive proofs work, right? Like you assume that the recursive call has worked and then you use it. Well, and recognize that that's going to happen all the way up. We're simply going to return the result of that statement. Now, I have one more question about this. I think this still looks very strange because the function wants us to return an integer. And yet, we're returning an assignment statement? Is that okay? Yeah? Yeah. So what he said, assignment statements by default return the result of the assignment, the thing that was being assigned, the value that was being assigned. This is the thing that allows for chained assignments. The reason I know that all of you know this is because when we designed assignment operators, when we overloaded assignment operators, we made sure that they returned a helpful value. So this is an example of an application of that knowledge. Okay, any question about that? So it actually doesn't surprise us that the result of that assignment statement, which is really under the hood just a function call, the result of that assignment statement returns the value of the right-hand side of it effectively. Okay, and so then our return can return what it needed to. Of course, you could decouple these things. Of course, you could say S of I equals find of S of I, return S of I if you wanted to. But you know what? I wanted to have that moment of review. So it works this way too. All right, any question about that? What do you think I'm going to ask you next? Yeah, what's the running time? That's right. So how well does this do? This implements that, that shortening the tree process. This implements path compression with almost no work at all. But the question is, how well does it do? What do you hope I say? You hope I say it makes what height trees? Constant height trees, right? Do you think we can? Do you think we can assure that our trees are constant height? Wouldn't that be incredible? Sadly. can't promise you that the trees are constant height. Such a letdown. I can't quite promise constant height trees. Okay? All right, well, let's see what we can promise then, okay? I want to take the time for a slight divergence and talk to you about a new function called the iterated log. So I have a recursive definition of the iterated log function given here. The English version is that it simply counts the number of times you can take log for a number. Okay? It counts the number of times you can take log. So for example, look at the recurrence. It tallies a 1 when it takes a log, and it bottoms out at 1. So it just effectively counts the number of times you can take log, okay? Now, this might be a new function to you, so I want to do a little bit of an example to give you a feel for how this function works. And we're going to do log base 2 because it's actually the fastest growing of the logs, okay? All right, so here's our example. How big is that number? How big is that number? Very big. In my right hand, I hold all the atoms in the universe. In my left hand, I hold that number. Which hand is bigger? Wait, which way does this tail? Oh yeah, way this way. In fact, I think it's true that that number is bigger than all the atoms in the universe plus the number of seconds that have the number of seconds since the beginning of the universe. Okay, I believe that that's true, but I don't know for sure. But it's on that scale, okay? That number is inconceivably big. You're certainly not going to make a computer with that much memory, okay? All right, but let's take the iterated log of it, okay, of this inconceivably large number. Well, iterated log is just a count of how many times you can take logs. So we better start by taking a log. What's the log of that? This inconceivably huge number. What's the log base 2 of it? Yeah, look, it's the population of Champaign. Right? Yeah. Okay. All of a sudden, you've got some function that, and that's just log. That's not even iterated log. All right, fine. What's the log of that? What is it? Anybody got it? The age of your little sister. Raise your hand if you have a sibling who's 16. Yeah. No, see? It's reasonable, right? Okay, what's the log of that? Log of that is the number of finals you have. The log of that is the number of hours of sleep you got last night. Oh. All right. So how many times did we take log? 1, 2, 3, 4, 5. So the iterated log star of 2, this inconceivably huge number is 5. Okay? So for all practical purposes, log star of any number is less than or equal to 5. That is, it's bounded above by a constant. Okay? We can find one. Well, except that eventually it's not, so you can't really argue it. Okay, so here's the result I do have for you. Yeah? Because it just it stops there. And you know what? I actually don't even care whether it's 5 or 6. Okay? I think it stops at 1. I think you stop there. Can't remember for sure. All right, so what's our result? How does this play into anything that's meaningful to us? So imagine that you have a disjoint sets structure that has n pieces of data in it, okay? Maybe it's huge. Maybe you're doing this on the pixels in an image or something. And you've got n is equal to 1,000,000, okay, say, okay? And you're going to use that structure for a while as kind of a query structure, right? To find keys and to see what sets to test membership of elements in this structure. Well, any sequence of m of those operations, okay, so as many as you want, use this structure for as long as you want, m of the m operations, results in worst case running time of big O of, I know that one of the factors has to be m because I'm doing m things. I'm doing m operations, okay? If each of these were constant time, I would stop there, right? If each of these were constant time operations, I'd say big O of m, right, for my total running time. They're not quite constant. In fact, the result is that it's big O of m times log star of n, where n is the number of items. So effectively, we can do m operations in big O of m time. It's just not quite accurate to say it that way. Okay? Any question about that? So this is really good news. Oh, here's something. This log star n right here, it actually grows much, much faster than the true function you can use here. The proof of, there is a proof, the tightest bound known for this is called the inverse Ackermann function. But it takes a little longer to describe. You have to start with the Ackermann function and then invert it. And so I chose this log star n, which is much, much bigger, much faster growing than the inverse Ackermann function. So actually, this is very close to constant time. Furthermore, every time I ask you for assessing the running time of these things, it will be safe for you to assume that they are constant time. So theoretically, they are not. Practically, they are. You can assume for when you're embedding this analysis in some larger argument, you can say that they are constant time and we won't ding you for it. Okay? So that's good news. That means we've got this complex structure where both operations effectively run in constant time. Yeah? Uh-huh. Yeah, that's what I meant. That's exactly what I meant, okay? So we say that this is pretty much big O of m for m operations, or a total of big O of 1 per operation, okay? All right, anything else about this? Okay. I don't remember what that link is. It was just there and I didn't get rid of it. All right, so we've thrown at you priority queues, disjoint sets. They're going to be useful to us in designing graph algorithms. In order to get to those graph algorithms, I need to spend some time just getting us going on graphs. Now, for vocabulary purposes and fundamental constructs and definitions, I'm going to assume that you had CS 173. Next time, I'm going to give you a list of terms that you really should understand and understand mathematically so that you can go through and kind of check your own recollection based on your experience in the discrete math class. So this is the moment where the discrete math prerequisite is real. But I'm going to spend today talking about applications of graphs, because everybody knows, everybody in our world agrees, graphs are the best data structure. Okay, and I want you to feel that way too. I'm not even sure I really feel that way. All right, so I have a whole bunch of graphs, and we're just going to spend the rest of the day talking about them. Any guesses as to what this one is? Universe? Nope. Yeah, it could be, but it isn't. It isn't. It's the byline at the bottom of it didn't say that. Yeah? The internet, it's the World Wide Web. So it's the websites from 10 years ago. Okay? So this is an artist's impression of the World Wide Web 10 years ago. Now, I'm pretty sure that if we did that same, did that same design now, it would like cover the ceiling of this room or something, or probably even more, right? Like, I don't know what the scale is, but it's grown amazingly much. So we kind of have this understanding of the World Wide Web as a graph, and we can look at this and see it pictorially represented as such. But if we're going to talk about the web as a graph, we have to draw an identity between the vertices and the picture and the edges and the picture. Vertices and the application and the edges as the application. So let's do that. So in this case, the vertices are websites. And there's an edge UV if site U links to site V. Okay? Now, based on that description, your first thought should be, oh, it's a directed graph, right? Because just because I link to you does not mean you link to me. All right? So there's a little teeny tiny bit of vocabulary there. Let's see. All right. So what's the power of a mapping like this, where these things are mathematical constructs related to the graph as a combinatorial object, and these things are something that exists in the real world that we have to engineer, right? So here's the thing. If you know something about the real world, you can ask interesting questions of your graph based on what you need to know for the real world. If you know something about graphs, you can offer suggestions about how things should be done in the real world. So the connection between the two, the mapping from the application to the mathematics, is deeper than just labeling things as vertices and edges. It goes beyond into algorithms. All right, so I think this story, the story behind this graph, illustrates that as well. So let me tell you a little bit about this graph. Vertices in this graph are courses at a university. So the vertices are courses. And there's an edge UV if, well, raise your hand if you are simultaneously enrolled in this class and CS233. Okay. Because one of you raised your hand, there would be an edge between 225 and 230. Well, let's do it this way. 233 and 225 in this graph, because we're just, we're all that. So there is an edge between the two classes. Now, why would we ever want to do that? So this is some student is in both classes. So here's the implication. If you schedule the CS225 and the CS233 final at the same time, you will have to offer a conflict exam. Okay? Does that make sense? Because some student would need to be in two places at once. So what this graph is the basis for a labeling of the vertices so that no two adjacent vertices are labeled the same way, and then each label type is a final exam time slot. Okay, so all of the red squares, maybe those are the exams that take place Friday morning at 8 a.m. Maybe these are Friday morning at, wait, when's the next one? Friday at 12:30, etc. Okay, maybe these are Monday at whatever, okay? So if you can label the vertices like this, you will have no conflicts. This is called a conflict graph. The goal then becomes label the vertices so that no two adjacent vertices are labeled the same, color or shape or whatever. And use as few of those labels as possible. Okay, so let me write part of that down. Using as few labels as possible. Label the vertices. So no two adjacent are same. Okay? This is called a graph coloring. This is called the graph coloring problem. And you would think that every university, you'd think there'd be some little tool you can buy, something you can plug into Compass that would hypothesize a final schedule for every university that uses that software, right? No, guess what? There is no good algorithm for finding a graph coloring. There isn't one. No efficient algorithm exists for finding a graph coloring. So this problem itself, even though it's easily posed, easily understood, this problem is a class of problems for which no known efficient algorithm exists. You'll study the characteristics of such problems in 374. Okay? Those are called the NP-complete problems. And complexity will be part of that class, is a significant part of that class. Yeah? I'm not going to answer that question. That's like taking the conversation in a different direction, okay? Okay. All right, any questions about that? So even though we can pose a question easily, we can't answer it necessarily. Okay, so the graph up here is, I found it when I was looking for this. It is a model of the play Titus Andronicus. The vertices are characters in the play. There's an edge between a pair of vertices if characters share stage time, and the size of the vertex is the amount of stage time that each character uses. Now, I cannot look at that graph and tell whether there is any literary value to it. But you know what? I'm a computer scientist. I'm not a literature scholar, right? And so what might be true is that somebody whose expertise is Shakespearean literature may be able to look at that graph and go, oh, I never knew. And what this says to me is that, what it emphasizes to me is the need for people who work in the humanities and those of us who view things algorithmically and structurally to talk to one another to see if there are inferences that can be drawn from the structures that humanities scholars build on their own. Music composition is another area. I have a friend who's a faculty person in music. He does music composition, and he has this very elaborate grammar for doing composition. And every single piece of it is a data structure that you can put a label on and study in one of our courses. And I'm pretty sure, well, I know it's true that I know absolutely nothing about music, and I'm pretty sure he knows nothing about computer science, and yet we could have pretty interesting questions if we kind of poke at each other's understanding. So my point here is that opportunities for applying your craft abound, even in places you might not expect. All right, any guesses what this is? No? Okay. So you have one of these too, and the interesting research result is yours probably looks a lot like mine. This one is mine. What is it? Mine's probably got more clumps because I'm older. Yeah, this is my Facebook network 10 years ago. Okay, this is early days. I mean, maybe not 10, but lots, quite a while ago, at least 5 years ago, okay? So what's interesting about this, here's U of I. This is, my hometown. You have those two clusters. You know they do. You do. This is my family. This is my sister. She knows this, yeah. I don't know who this is, but I need to find out, right? I need to figure out who this person is right here. I don't know. They're like, they've got their, I don't know. This right here is these are my roller derby friends. They're kind of a clique. That's a joke. I'm sort of ostracized. I mean, I'm not ostracized, but I'm not part of that clique anymore because I realized I was going to get hurt. So I'm like, I'm out. You guys are coming to hit me. I don't want to play. All right. Raise your hand if you have played this game. So anyway, so you can all make your own Facebook graphs. Wolfram Alpha actually does a better job than that app did. All right, so raise your hand if you've played this game. Okay, so you're going to have to help me with this because I always kind of forget how it goes. So this is called Rush Hour, right? And I believe, correct me if I'm wrong, but I believe the goal is to get that red car off the board. Furthermore, I believe that cars can only move forward and backward, right? Can they go out the door? None of the cars go out the door except the red one. You just have to get them out of the way. Oh, that was the part I messed up before. Okay, there is a door right here, and it's the only place that red can come out, okay? So the goal is just to get that red car off of here. That's the game. What's the graph? The heck? And to tell me what that graph is, I want a description of what the vertices are and what the edges are. What are the vertices in that graph? Yeah. Very good. Okay. So he said that the vertices are states of the board. I'm going to say board configuration because I don't know about state exactly. So I'm going to say a board configuration. And there is an edge between if you can get from one board configuration to another by a legal move. So building this graph is already interesting. All right, fine. What are the green dots then? The green dots are a solution path, right? Where do you think the start is? Where's the start? So when you play this game, you get a little card that tells you the initial board configuration. Where is that? Is it this one or one of those? It's this one because you only get one starting board configuration, right? And so then you follow the green dots via the edge, via the moves that are between them, and it takes you through the solution. So what's going on at the top? Yeah, there are a bunch of different solutions, and this must be, I haven't played it, but this must be one of those games where, you know, once you get to this point, you're kind of home free, right? There are lots of different ways you can finish off the game at the end, okay? We're going to be looking at algorithms to find not only a path in a graph like this, but also a shortest path. It's just traversal. We just need to be able to walk around on the graph looking for a solution. All right, any question about that? Okay, I love this one because when I was in, I don't know, 4th grade or so, and this was probably true for you too, somebody gave you strategies for determining divisibility for all the numbers, right? How do you tell if something's divisible by 2? If it's even, right? You look at the last digit. How do you tell if something's divisible by 3? So he said the sum of digits is divisible by 3. How do you tell if that number is, if the sum of the digits is divisible by 3? The sum of the digits. I assert this was your first recursive function. Right? Oh. You knew this trick before you knew factorial. And this one was meaningful. This was a shortcut. Okay? All right, fine. 4. Last 2 digits. That's right, because 100 is divisible by 4 is basically all that's telling you. 5. 5 is easy peasy, right? 0 and 5. 6. Yeah, that's like a, you write the algorithm, right? It's an and, it's a conjunction. 2 and 3. All right, fine. 6. Here's where I got mad when I was a child. My teacher had no solution for 7. Now, some countries, apparently, in their math curriculum will talk about this, about a way of doing divisibility by 7, but I never knew it. And so when I was looking for graphs and I stumbled upon this one, I was like, yes, finally, an automatic way for detecting divisibility by 7. Here's how it works. You start at 0, and you're basically going to process a number, 3,703, as a string of digits. And the way you do it is you follow, and you're going to do it left to right. So for this 3, you follow blue 3 arrows followed by a red arrow. And then you move to the next one. So we're going to go 1, 2, 3, followed by a red one. After reading the 3, I'm in that state. Then I read a 7. Now I follow 7 blue arrows followed by a red arrow. So 1, 2, 3, 4, 5, 6, 7, followed by a red arrow, and I move here. Then I move 0 blue arrows followed by a red arrow. Then I move 3 blue arrows, 1, 2, 3 blue arrows followed by a red arrow, and we end up here. So 3703 is divisible by 7. Yes! That's a graph. I haven't dug into this very deeply. There's a little bit of number theory in here. It's a finite state machine that reads inputs. I suspect that the states are residuals mod 7, right? The remainders mod 7. But I haven't dug into the number theory too much. So there you go. This one is, I'm not going to have time. So this bunny is based on a famous data set. Meshing algorithms and lots of computational geometry algorithms actually are graph-based, and I wanted to bring that into the story. But I want to finish the story by telling you the cosmic thing that happened. So this data set is just a whole bunch of points that somebody took from some bunny in the 70s. And graphics algorithms now use that data set as a benchmark. So you'll always find different attempts at algorithms based on that bunny. So imagine my surprise when I was at my aunt's house in her family room looking at her bookshelf, and on her bookshelf was the bunny, the very same bunny. I was like, oh my gosh, I'm in the presence of something famous. Now, of course, it turns out that there are a million of these mass-produced bunnies, but I thought it was still kind of cool nonetheless. That's all I really have. We'll start doing serious graph stuff next time. What's up?
Friday.